Welcome to today's problem walkthrough. We'll be exploring problem number 1204, last person to fit in the bus. This problem is a great exercise for thinking about edge cases and constraints in algorithm design. Let's dive into the details and solve it step by step. In this problem, we are tasked with determining the last person who can board a bus without exceeding its maximum weight capacity. The bus has a predefined weight limit, and passengers waiting at the stop each have their own specific weights. The input includes a list of these weights, where each value represents the weight of an individual passenger, and an integer representing the bus's total weight capacity. The goal is to find the one-based index of the final person who can board the bus before the total weight surpasses the capacity. For the first example, the weights of the passengers are given as 100, 200, 150, 80, and the bus's weight capacity is 300. The bus starts picking up passengers in order, adding their weights cumulatively. The first passenger, weighing 100, boards successfully, bringing the total to 100, which is within the capacity. The second passenger, weighing 200, boards next, and the total becomes 300, still within the limit. However, when the third passenger, weighing 150, tries to board, the total weight increases to 450, which exceeds the bus's capacity. As a result, the last person who successfully boarded without breaching the limit is the second passenger, so the output is 2. In the second example, the weights of the passengers are 50, 50, 50, 50, and the bus's capacity is 200. Here, the bus proceeds to pick up each passenger in order. The first boards with a weight of 50, making the total 50. Next, the second passenger boards, bringing the total to 100. The third follows, increasing the total to 150. Finally, the fourth passenger boards, and the total becomes exactly 200, which is still within the capacity. Since all passengers fit on the bus, the last person to board is the fourth passenger, making the output 4. In the third example, the weights are 120, 80, 70, 60, and the bus's capacity is 150. The bus begins by picking up the first passenger, who weighs 120, bringing the total to 120, which is within the capacity. When the second passenger, weighing 80, attempts to board, the cumulative weight rises to 200, which exceeds the limit. Therefore, the last person who fit on the bus before the capacity was breached is the first passenger, so the output is 1. The problem comes with several constraints and edge cases. The number of passengers can go up to 10,000, and their individual weights can range from 1 to 10,000. The bus's capacity can be as large as 1 billion, so the solution must handle large inputs efficiently. Notably, the problem guarantees that at least one passenger will fit on the bus. For edge cases, if there is only one passenger, they will either fit or not, but the output is always their index. If all passengers fit within the capacity, the output corresponds to the last passenger's index. Additionally, the scenario where the first passenger exceeds the capacity is not possible due to the guarantee that at least one person will fit. Ultimately, the aim is to simulate the boarding process, track the cumulative weight, and determine the index of the last passenger who successfully boards before the capacity is exceeded. When tackling this problem, we considered multiple approaches, starting with the brute force method. The intuition here is straightforward. We iterate through the list of passengers, adding up their weights one by one as they board the bus. The moment the total weight exceeds the bus's maximum capacity, we stop and identify the last passenger who was successfully added as the solution. This approach relies on maintaining a running sum of weights to determine when the limit is crossed. The key advantage of this method is its simplicity. It only requires a single pass through the list of passengers, giving it a time complexity of O(n). However, there are trade-offs. While it's effective when passengers must board in the given order, this method doesn't account for scenarios where rearranging passengers could fit more people on the bus. This limitation makes it less suitable if the goal is to optimize the total number of passengers, but for a fixed order, it remains efficient and straightforward. Another approach we considered is a greedy strategy. Here, we start by sorting the passenger weights in ascending order. The idea is to prioritize lighter passengers first, which maximizes the number of people who can fit on the bus. Once the weights are sorted, we iterate through the list while maintaining a running total of weights. As soon as adding another passenger exceeds the bus's maximum capacity, we stop and return the last passenger who was successfully added. Sorting the weights ensures that we maximize the use of the available weight limit, but it does introduce an n log n computational overhead due to the sorting step. This makes it slightly more resource-intensive than the brute force approach, especially for smaller datasets. However, for larger datasets, it provides a more optimized solution in terms of maximizing the number of passengers, assuming the boarding order is flexible. Despite its advantages, it's important to note that this approach isn't suitable if the passenger order is fixed, as the sorting step would violate that constraint. We also explored an alternative approach using dynamic programming, which treats the problem as a variation of the 0/1 knapsack problem. In this method, we aim to find the optimal subset of passengers that maximizes their count while staying within the weight limit. This approach considers all possible combinations of passengers, making it highly comprehensive. However, the computational complexity is significantly higher, with a time complexity of n*W, where W represents the maximum weight capacity of the bus. While dynamic programming is powerful and ensures an optimal solution, it's often unnecessary for this problem. The task explicitly focuses on identifying the last passenger to board, which doesn't require the complexity of evaluating subsets. For this reason, the dynamic programming approach is more suitable for problems that demand maximizing the number of passengers or optimizing other constraints, rather than simply determining the last passenger who fits. After evaluating these methods, we chose the brute force approach as the most appropriate strategy for this problem. This decision aligns with the problem's constraints, which emphasize determining the last passenger who can fit in the bus, given a fixed boarding order. The brute force solution is both simple and efficient, requiring only a single pass through the list of passengers to maintain a running sum of weights. This makes it computationally optimal, with a time complexity of n. In contrast, the greedy and dynamic programming approaches add unnecessary complexity. The greedy method, while effective for maximizing the number of passengers, isn't applicable here since the boarding order is fixed. Similarly, the dynamic programming approach, though comprehensive, is overkill for this straightforward problem. By prioritizing simplicity and efficiency, the brute force method directly addresses the problem requirements without introducing additional overhead. To summarize, the brute force approach is the optimal solution for this problem due to its clarity, simplicity, and efficiency. It effectively handles the fixed boarding order while maintaining the computational requirements at n. Alternative methods like greedy strategies or dynamic programming might be more suitable for different variations of the problem, such as optimizing the total number of passengers. However, given the task's focus on finding the last passenger who can fit, the brute force method strikes the right balance between functionality and performance, making it the best choice here. In this problem, we are tasked with determining the maximum number of passengers that can board a bus without exceeding its weight capacity. To achieve this, we need to evaluate an array of passenger weights and ensure that the cumulative weight does not surpass the bus's maximum weight limit. The solution involves a step-by-step approach, starting with input validation. Here, we ensure that the list of weights is not empty and that the maximum weight capacity is a positive integer. If the input fails these checks, the algorithm will return 0 or an appropriate error message. Next, we initialize two key variables. The first is current_weight, set to 0, which will keep track of the cumulative weight of passengers boarding the bus. The second is count, also set to 0, to record how many passengers have successfully boarded. These initializations set the stage for processing the passenger weights iteratively. The next step involves iterating through the list of passenger weights. For each passenger weight in the list, we check whether adding the current passenger's weight to the cumulative weight would exceed the bus's maximum capacity. If it doesn't, the weight is added to current_weight, and we increment the count variable to reflect that one more passenger has boarded the bus. However, if adding the current weight would exceed the maximum capacity, we immediately stop processing further passengers by breaking out of the loop. This ensures that no additional passengers are considered once the weight limit is reached. After the loop completes, the value of count is returned, representing the maximum number of passengers that were able to board the bus without exceeding its weight limit. This algorithm has several key characteristics. First, it follows a greedy approach, as passengers are processed in the given order, and the algorithm stops as soon as the maximum weight capacity is breached. This makes the solution efficient, as it avoids unnecessary computations. Additionally, the algorithm handles edge cases effectively. If the weights array is empty, the output is 0 since there are no passengers to board. If a single passenger's weight exceeds the bus's maximum capacity, no passengers will be able to board. On the other hand, if the total weight of all passengers is less than or equal to the bus's capacity, then all passengers can board successfully. The solution is also space efficient, as it relies on the input array and just two variables, current_weight and count, to keep track of progress. When analyzing the algorithm's complexity, we see that its time complexity is O(n), where n is the number of passengers. This is because each passenger's weight is processed exactly once. The space complexity is O(1), as the algorithm only uses a few variables regardless of the size of the input. Let's look at a few edge case examples to clarify. If the input is an empty list of weights and the maximum weight is 100, the output is 0 because there are no passengers to consider. If the list contains a single passenger whose weight is 120, but the bus's maximum capacity is 100, the output is also 0 because the passenger exceeds the weight limit. Lastly, if the weights are 10, 20, 30, and the maximum weight is 100, the output is 3 since the total weight is 60, which is well within the limit, allowing all passengers to board. There is potential to optimize this algorithm further. For example, if the passenger weights were sorted in ascending order, we could use a binary search to determine the maximum number of passengers that can board. However, this optimization requires pre-processing the input by sorting it, which increases the overall time complexity to O(n log n). To illustrate the algorithm in practice, let's walk through an example with the input weights 30, 20, 50, 40, and a maximum weight of 100. First, we initialize current_weight and count to 0. The first passenger, with a weight of 30, can board since the cumulative weight remains within the limit. We update current_weight to 30 and count to 1. Next, the second passenger, with a weight of 20, also boards, bringing the cumulative weight to 50 and count to 2. The third passenger, with a weight of 50, can still board, reaching the maximum weight of 100 and incrementing count to 3. Finally, when we consider the fourth passenger, who weighs 40, adding this weight would exceed the bus's capacity, as the cumulative weight would become 140. At this point, we stop processing further passengers. The algorithm terminates, and the final output is the value of count, which is 3. This means that the maximum number of passengers who can board the bus without exceeding the weight limit is 3. This example highlights the algorithm's efficiency and its ability to handle scenarios where passengers must be excluded once the weight limit is reached. The solution begins by defining a function lastPerson to fit within the solution class. This function takes two inputs, weights, a list of integers representing the weight of each person, and capacity, an integer representing the maximum weight the bus can hold. We initialize two variables, current_weight, set to 0, which keeps track of the total weight of passengers currently on the bus, and last_person, set to -1, which will hold the index of the last person who can board the bus without exceeding the weight limit. The function then iterates over the weights list using a standard for loop. At each iteration, it checks if adding the current person's weight to the total, current_weight plus weights, I, will exceed the bus's capacity. If not, the person's weight is added to current_weight, and last_person is updated to the current index I. If adding the weight would exceed the limit, the loop breaks early because no further passengers can board. Finally, the function returns the value of last_person, which represents the index of the last passenger who was able to board the bus without exceeding the weight capacity. If no passengers could board, last_person will remain -1, as initialized. This solution runs in O(n) time, where n is the number of people, since it involves a single pass over the weights list, making it efficient and straightforward. This is the Java implementation for LeetCode problem number 1204, last person to fit in the bus. The logic mirrors the Python implementation, where we iterate through the list of weights, adding each person's weight to the cumulative total until the bus's capacity is exceeded. Key differences include Java's use of type declarations, the int, array for input, and the explicit for loop. The method returns the index of the last person who can board the bus without exceeding the capacity. Here, we're presented with example 1, where the weights of the people are 50, 30, 20, 10, and the bus capacity is 100. We start by initializing two variables. Current underscore weight is 0, which will keep track of the total weight on board, and last underscore person is -1, which will store the index of the last person who successfully boards. In the first iteration, we check if adding the weight of the first person, 50, keeps the total weight within the capacity. Since 50 is less than or equal to 100, we update current underscore weight to 50 and set last underscore person to 0. In the second iteration, we add the next person's weight, 30, to the current total. The sum is now 80, which is still within the capacity, so we update current underscore weight to 80 and last underscore person to 1. In the third iteration, we add the next person's weight, 20, to the current total of 80. This brings the total to exactly 100, which is equal to the bus capacity, so we update current underscore weight to 100 and set last underscore person to 2. Now, in the fourth iteration, we check if adding the final person's weight, 10, would exceed the capacity. Since 100 plus 10 is greater than 100, we cannot add this person, and the loop breaks. The final output for this example is last underscore person equals 2, meaning the third person, at index 2, is the last one who can fit on the bus. In example 2, we explore an edge case where the weights are 40, 60, 30, and the capacity is 100. Starting with the same initialization as before, current underscore weight is set to 0 and last underscore person to -1. In the first iteration, we check if adding the first person's weight, 40, keeps the total within the capacity. Since 40 is less than or equal to 100, we update current underscore weight to 40 and set last underscore person to 0. In the second iteration, we add the next person's weight, 60, bringing the total to exactly 100. This is still within the capacity, so we update current underscore weight to 100 and set last underscore person to 1. Now, in the third iteration, we check if adding the final person's weight, 30, would exceed the capacity. Since 100 plus 30 is greater than 100, this person cannot board, and the loop terminates. The final output for this example is last underscore person equals 1, meaning the second person, at index 1, is the last one who can fit. In example 3, we look at a scenario where no one fits. The weights are 150, 200, 300, and the capacity is 100. After initializing current underscore weight to 0 and last underscore person to -1, we check the first person's weight, 150. Since 150 exceeds the capacity, no one can board, and the loop ends immediately. The output for this final example is last underscore person equals -1, indicating that no one could fit on the bus. It's important to note that the algorithm terminates as soon as adding the next person would exceed the bus capacity, ensuring efficiency. The variable last underscore person is updated only when a person successfully boards, allowing us to accurately track the last person who fits. If no one fits, it remains -1. The runtime complexity of this algorithm is O(n), where n is the number of people in the weights list, since we iterate through the list only once. Here, we analyze the time complexity of the solution, which is O(n), where n represents the number of elements in the weights array. The key reason for this is that the loop iterates over each person's weight, and in the worst-case scenario, it will process all n elements until either the bus reaches its weight capacity or all weights are evaluated. Within each iteration, we perform constant time operations, adding the current weight, comparing it with the capacity, and updating the last person index. Since these operations take O(1) time individually, and the loop runs at most n times, the overall time complexity is O(n). In terms of best, average, and worst-case scenarios, the best case occurs when the first person's weight exceeds the bus capacity, causing the loop to terminate immediately, which results in O(1). The average case depends on how many people fit on the bus before reaching capacity, leading to OK, where k is typically less than n. Finally, the worst case is O(n), where all weights are processed because their cumulative weight does not exceed the capacity until the very last person. Now, let's discuss the space complexity, which is O(1), meaning the algorithm uses a constant amount of memory regardless of the input size. This is because the solution only relies on two integer variables, one to keep track of the cumulative weight, and another to store the index of the last person who fits. No additional data structures, such as arrays or lists, are used, and the input weights array is treated as read-only. Since no extra space is allocated and the memory usage remains fixed, the space complexity is constant, or O1, which further highlights the efficiency of this approach. To put this into perspective, let's compare the current solution with a brute force approach. A naive method might involve testing all possible subsets of the weights array to determine the maximum number of people that can fit without exceeding the capacity. This would require examining O2 to the power of n subsets, which is computationally expensive. In contrast, the current solution is much more efficient, as it processes each weight only once, achieving O(n) time complexity. This approach is already optimal for the problem, as it minimizes both time and space complexity. To solidify this, consider the big O proof. The loop runs at most n times, with each iteration involving O(1) operations, resulting in an overall time complexity of O(n). Additionally, the use of only two integer variables ensures a space complexity of O(1), regardless of input size. In conclusion, this solution is both time and space efficient, making it well suited for solving this problem even at scale. When solving problems like this, it's essential to watch out for common mistakes that can trip you up. One major issue is not accounting for edge cases. For example, you might forget to handle scenarios like an empty list of passengers, edge case weights such as 0 or the maximum possible weight, or situations where no valid configuration exists. These are the types of scenarios that can lead to runtime errors or unexpected outputs. For instance, if the problem includes a weight limit per bus, an empty input or improperly handled edge case could cause your solution to behave incorrectly. Another common pitfall is relying on brute force solutions without optimizing them. While brute force might work for small test cases, it quickly becomes computationally expensive as the input size grows, often leading to time limit exceeded errors. For example, iterating through all combinations of passengers is unnecessary if a more efficient approach, like a greedy or sliding window method, can be applied. Lastly, be careful with summation logic. It's easy to mismanage cumulative weights or forget to reset the sum at the right point in your algorithm, such as when a bus reaches its capacity. Missteps like these can lead to incorrect results, so always double-check how you're handling these resets. Now, another potential issue to be mindful of is overlooking the constraints specified in the problem. For instance, if there's a maximum passenger or weight limit per bus, ignoring these constraints can cause your solution to fail under stricter test cases. You might assume, for example, that all the input weights will fit into a single bus, but unless the problem explicitly guarantees this, such assumptions can lead to errors. Additionally, the choice of data structures plays a significant role. Using inefficient data structures, like lists where queues or heaps would be more appropriate, can unnecessarily increase the time complexity of your solution. From an interview perspective, it's critical to thoroughly understand the problem's constraints. Interviewers often test edge cases, so you should be prepared to explain how your solution accounts for them. A good strategy is to break the problem into smaller steps. Starting with a brute force approach can help clarify your understanding before you optimize it. When optimizing, make sure to communicate the trade-offs of your approach, especially when balancing time versus space complexity. Recognizing patterns is also key. Many problems involving buses, passengers, and weights can be solved using greedy algorithms, sliding windows, or two-pointer techniques. Identifying these patterns early can streamline your problem-solving process. Finally, always test your solution incrementally. Start with small inputs and edge cases, and ensure your logic works before scaling to larger datasets. To deepen your understanding of this type of problem, it can be helpful to explore related problems. For example, LeetCode 1011, Capacity to Ship Packages Within D Days, involves a conceptually similar challenge of partitioning packages onto ships. Similarly, LeetCode 410, Split Array Largest Sum, and LeetCode 875, Cocoa Eating Bananas, both deal with optimizing resource allocation under constraints. Another interesting problem is LeetCode 1891, Cutting Ribbons, where the goal is to maximize partitions based on given criteria. These related problems often share foundational techniques and offer valuable practice. Speaking of techniques, alternative approaches like the greedy algorithm can be highly effective. In scenarios where the order of passengers or items matters, a greedy approach allows you to minimize complexity while ensuring correctness. For example, it can help reduce the number of buses or trips needed. However, it's important to note that while greedy methods are efficient, they don't always guarantee the most optimal solution, especially in problems requiring exact partitioning. Another powerful tool is binary search, particularly for problems that involve minimizing or maximizing a value, such as finding the minimum bus capacity. Binary search works well in these cases because it leverages the monotonic property of the solution space. However, it's not universally applicable, as the problem must exhibit this monotonicity for the approach to work. Finally, let's consider dynamic programming, which can be a game changer for problems involving partitioning or subset sums. DP is particularly useful when you need to explore all possible configurations to find an exact solution. For instance, it can help determine how to distribute weights across multiple buses while adhering to constraints. However, the trade-off with dynamic programming is its higher space and time complexity compared to greedy or binary search approaches. As a result, while DP can provide precise solutions, it's essential to evaluate whether its computational overhead is justified for the given problem. By understanding when to use techniques like DP, binary search, or greedy algorithms, you'll be well equipped to tackle a wide range of problems efficiently and effectively. Thank you for watching this walkthrough. Remember, every problem you solve helps you grow as a coder. Today, we learned how to approach and optimize a solution for a real-world inspired problem. Keep practicing, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!